Welcome everybody. Today we begin the normal distribution, the most important continuous distribution in statistics. Let's start with the idea of a continuous random variable. A continuous random variable can take any value in an interval, no jumps, no gaps, just a smooth range of possibilities. Think about height, weight, blood pressure, all of these smooth measurements. Now, many real-world measurements tend to cluster around a center, and when that pattern becomes symmetric and bell-shaped, we call it normal distribution. This shape is powerful. It lets us make probability statements very quickly. This curve shows up everywhere, in nature, in human behavior, in measurements error. It becomes the foundation for almost everything we do later: confidence intervals, hypothesis tests, and more. So what makes a distribution normal? A distribution is normal if it is continuous, symmetric, unimodal, and bell-shaped, exactly like that shape we are seeing here. And in this case, we are saying our random variable x is following the normal distribution with mean mu and variance sigma square. Every normal curve is defined by two parameters: the mean, which we are gonna use mu for it, and this is where the center is. And if the mean was positive, then the whole curve would be located to the right of your zero. However, if it is a negative mean, you will find the whole curve is located to the left of the zero. So the curve is moving right or left upon the sign of our mu, or the mean. And the other parameter is the standard deviation sigma, and this actually represents the spread in my curve, and it controls actually how wide or narrow the curve is. On this graph, we do have a peaked or a narrowed curve, and the other one is not narrow, it's wide. And notice here the difference is actually not just in the mean, of course, because the mean here is 40, so it's shifted more to the right than the first one, which is having a mu or a mean of 10. However, that shape, narrow and wide, depends actually on the value of my sigma. Here it's 2.5, so more narrowed, and here it's 5, so it is wide. And again, it represents the spread. So this visual meaning is important because everything we do next depends on these two parameters. Now that we know what mu and sigma represent, we can understand the empirical rule. About 68% of the values fall within one standard deviation from the mean. So if this is mu plus sigma and this is mu minus sigma, I do have here 68% underneath the curve, that area, while 95% lie within two standard deviation from the mean. So if I move these boundaries to mu plus 2 sigma and mu minus 2 sigma, so within 2 sigma, I will have 95% of the total area under the normal curve. And lastly, almost all values fall within 3 sigma from the mean. So if I just stretch my boundaries to be at mu plus 3 sigma and mu minus 3 sigma, within 3 sigma, I will find almost all the area under the curve between these two boundaries. This gives us a quick, intuitive sense of spread. Now we will have as many normal distributions or normal curves as we will have combinations of mu and sigma. And to deal with all of these different normal curves, we need to convert them to a universal curve, which we are gonna call standard normal distribution. And here in that standard normal distribution, we will have a mean of 0 and a sigma or sigma square or equal to 1. And this curve, which is the standard normal curve, is actually the main player when we are gonna calculate probabilities. And we will do the actual z-score formula in the next lecture. What is the z-score formula? This is the z formula that will translate or convert my x with normal mu and sigma to a z, a standard normal random variable with normal centered at 0 and its variance and sigma is equal to 1. So that z-score, we are gonna talk about it in our next lecture. However, we are gonna now see how to read or quantify any probability for a standard normal random variable z that is following a normal 0, 1. So these probabilities, we are gonna read it from the standard normal table, which will give me always the area, the cumulative area to the left of a specific z value, and this z value could be positive or negative. So if z is positive, here it is to the right of a 0, so it's positive value. The area that I'm gonna read from my table is that area. And if z was negative, also the table will give me the area to the left of that negative z, and these are actually the probabilities that we would like to quantify. Now let's see this example. I want to find the probability of z less than a specific z value, which is 1.20. And I will use the table, the standard normal table, to quantify this probability. First, let me sketch the graph. So here is since this is z, so I am gonna graph the standard normal distribution, which is centered again at the 0 point, and this is a positive z value, so it will be to the right of my 0 at exactly that value. And I want to find the left area. I want to find all the probability of all these z values that are less than a specific positive value. So this is the target area that I want to find, which is find the probability of all the values that would be less than 1.20. So this is a left area, and our table gives us this area. So let we go and check that value, how to read this probability or this area from our table. So here is our table. I want to go and find in my table the value of z. This is my z, that is equal to 1.2. Notice that this half of my table is having all of my z negative, while this one is having all the positive ones. So I'm gonna search here. Now I do have z equal to 1.20. So I'm gonna read for these values, the positive values is gonna give me the whole number, which is 1.1. I don't want 1.1, I want 1.2. And the second digit of my z value, which is 1.20, that's 0, I'm gonna read it from here. So the labels of the columns is for the second decimal value, while the labels of the row or the header of my row is giving me the whole number and the first decimal value. So 1.2 sticking with to it the 0, the intersection of these two is gonna be the area to the left of the 1.2. So this is the probability of all the z's less than or less than 1.20. Now, as we did read it from our table, the value or the answer for that probability is 0.8849. So let's see how to get the probability of a right-tailed area. We want to find the probability of z greater than -1, and that we first again step is to sketch the area in your probability statement. So I'm gonna sketch again the area. Here is my standard normal distribution. Why I'm using the standard normal distribution? Because my random variable here is z, which is following the standard normal distribution, which is centered at 0. Now I want to put that value of my z, and this is -1, so on the real line of the numbers, it would be to the left of your 0. So here is -100, okay. And which area I am interested in? I am interested in the area where all of the z's are greater than -1. So this is the z-axis again, and here all of these z's are greater than -1. So this is the area that I want to find, or this is the probability that is being asked here in my statement. Okay, I can get from my z table only the area to the left, which is that tiny little white tail. So I can read under the -1 from my table here that white tail. However, I want the other tail, the right tail. First, I'm gonna get the left tail, which is the tiny little white tail here, and I'm gonna read it at -1. So I'm gonna go down and till I find the -1.0. So the whole number 1 and the first decimal is 0, while the second decimal, I'm gonna read it from the column headers, which is the first 1.00. So the intersection again with that column, first column, and the line that is having a header, or the row that is having a header of -1 is the left tail. So that left tail is having an area or a probability of 1587. Okay, 0.1587. So this is the white tail. The right, or the right tail, which is having these lines in it, is my target. This is nothing but 1 minus that area. Why? Because the total area under the curve is 1, and this is the complement of this right area is actually the complement of my left area. So according to the probability rules, I can get it by 1 minus the left area. So right area would be 1 minus the left area. And this, if we are gonna calculate that on our calculator, it's gonna give me 0.8. This is an 8, okay, 413. So to get a right area, I will read the left area from my table, then subtract it from 1 to get the right area. So let's see this new example. I do want to find the probability of z between -0.5 and 1. So the first step, as usual, is to sketch the area that I am interested in its probability. So I'm gonna put my z-curve. Again, why I'm talking about a z-curve? Because here my random variable is z. So this is a standard normal curve centered at 0. And this is the z line again. And I want to find the probability of all the z's between these two values. 1, which is here, positive to the right of my 0. This is my 1. and the minus half roughly here to the left of my 0. And I want the area in between these two boundaries, so exactly from minus 0.5 to 1. So I want to find that area or that probability. How? Again, using my table, standard normal table. But the standard normal table gives me only the area to the left. So if I went to my standard normal table at minus 0.5, it will give me that tail. Let me just say that one, which is that white one. Let we just put some that one, that blue tail, if I read under minus 0.5, and if I read under 1, it will give me again the area to the left of 1. It will give me all of that area. So reading from my table under 1 and minus 0.5 will give me two areas, the blue area and the green area. However, we want the area in between, and this is the difference between these two areas, green minus blue. So let me see our table. So let's see the area under 1. Here is my 1. It's positive, so I'm gonna read it under the positive part of my table. And here is the 1. It's 1.0 and 0. So I'm gonna take that value, which is the area to the left of 1 is 0.8413. And I want the other area, the smaller area, which was left to the minus 0.5. This is the negative part of my table, so I'm gonna go till I find the minus 0.5. And what is the second decimal of minus 0.5? It's the 0 again. So that column with that row, it has that probability, which is 0.3085. So these two are my two areas that I'm gonna subtract the smaller one from the bigger one to get the area in between my minus 0.5 and the 1. So going back to our graph, here is my graph. I got that area from my table and it was 0.8413, that green area, the bigger area, and we did read together the smaller area, which was, as we said, 0.3085. So smaller area is a blue one, bigger area is a green one, and actually our target from the beginning was to find the area in between from just minus 0.5 to 1. So the difference between these two is the answer. So the probability of my z between minus 0.5 and 1 is equal to 0.53. This normal distribution gives us a universal shape, a way to compute probabilities, and a foundation for all upcoming inference topics. It's actually the bridge between raw data and standardized comparisons. So in our next lecture, we'll learn how to translate any value into this universal language using the z-score. See you next time, and thank you for being here.